Good morning. Today we are going to discuss about statistical quality control. From chapter 1, we are talking about production system, which consists of input, transformation system, output, and then the last one that we have never touched, that is the monitoring and control. And today, this issue will be focused. This is the production line or production process. You can see that when you put on the input here, and then there are some process, okay, around here, and before it becomes the finished good, you need to inspect the quality of the product to find two kinds of variation, that is a chance variation and assignable variation. So for the chance variation is variability built into the system. It's caused by random. Okay. So normally all the process consists of random variation. Okay. So if the process consists of just only the random variation, it means that the process is in control. And sometimes there might be some unexpected event occur in the system, like machine breakdown, worker absenteeism, something like that, okay? And that cause problem in the production system. We call that kind of variation as assignable variation. Whenever there is the assignable variation in the system, we call the process is out of control. For the quality control, it is going to seek for the assignable cause or assignable variation, so that whenever we find the out of control status, we need to perform the corrective action. In order to find the chance variation and assignable variation, we use the tools that is called control charts. These tools was developed in 1920 by Dr. Walter Shewhart. Sometimes we call it control chart and sometimes we call it Shewhart chart. This chart is going to be used to distinguish between chance variation and assignable variation. For chance variation, that is natural or random variation, if there is nothing wrong in the system will be consist of chance variation only. But if there is something wrong in the system, that is the assignable variation exists in the system and the system is being out of control. For the repetitive operation, this system will not produce exactly the same output. For instance, suppose you measure something, you measure the diameter of the pen, right? Okay, so you can see that there will be some variation, but the variation might be very little. Okay, that is so if the pattern of variability is normally described by normal distribution like this one. So if you want to plot the distribution for random sample, okay, so you plot it on the control chart. Okay, this is the control chart. We got two limits. This is the upper control limit or UCL and the lower control limit or LCL. So normally we take the sample, okay, and then we plot the mean of the sample in the control chart. And if all the data is between UCL and LCL, it means that the process is in control. Otherwise, if it go beyond UCL or lower than LCL, it means that the process is out of control. The UCL, the distance between UCL and LCL is 6 sigma plus 3 sigma here and plus 3 sigma here, right? The area under the 3 sigma distribution plus and minus 3 sigma of the normal distribution is 99.74%. Alright, okay, so normally if the process is in control, it will be within plus and minus 3 sigma here. So now you are going to build or construct two charts, that is X bar chart and R chart, in order to detect the whether or not the process is in control or out of control. You need to draw two charts. And this is in order to draw the X bar and R chart, you need to compute X bar, we call it X bar, that is summation of X bar and divide by the number of sample M. Orange, X max minus X min. R bar is the summation of R from R1 to Rm divided by M. And this is the formula that you are going to use in order to find UCL and LCL and center line for X bar and R chart. So you can see that there are 3 parameters that you need to find, that is A2, right, and D4 and D3. These parameters can be found from appendix table 6. Is going to be here. A2, D3, D4, right? A2, D3, D4. And in order to find the correct parameter for A2, D3, and D4, you need to find the number of observations in the sample, right? For instance, suppose in each sample you have to take 5 subsample, okay, that is 5 observation. So in that case, A2 is equal to 0.577 and D3 is equal to 0 and D4 is equal to 0.115. So let me give you some example. Okay, we have the piston ring for an automotive engine are produced by forging process. We wish to establish statistical control of the inside diameter of the ring by using X bar and R chart. 25 sample, okay, each of size 5. We take 25 sample and each of the sample consists of 5 observation. 5 observation, meaning that all the parameter should be come from n equal to 5. And we need to find whether or not the process is in control or out of control. So for sample number 1, we take 5 sub-sample or 5 observation. Okay, we take 1, 2, 3, 4, 5. We measure 1, 2, 3, 4, 5 piston and then record it on the table, in the table. And then we got 25 sample, right here, 25 sample. Each has 5 different observation. So X bar, XI bar, 74.010 come from 74.030 plus this one, this one, this one, and this one, and divide by 5, you got this, right? And for R1, I equal to 1, 0.038 come from maximum is 74.03 minus the minimum is 73.992. So you got this one, right? So for each sample, you need to calculate xi bar and ri, right? Because you got 25 sample, you have to calculate x bar I for 25 times and ri for 25 times as well. And then you need to find x bar bar. X bar bar comes from summation of xi bar, I from 1 to 25 and divide by 25. You got this one, right? 74.001. And r bar compute from summation of ri divided by divide by m, right? Okay, summation of this column, okay, and divide by 25. You got r bar of 0.023. All right. So now you need to draw the x bar and r chart. First, normally you need to start from r chart and then continue x bar, right? Okay. So let me start from r chart, r control chart. Using the data in the table, we find that the r bar is equal to 0.023. 0.023 is here, right? And then n is equal to 5, come from the number of observation per sample is equal to 5, 1, 2, 3, 4, 5. And then when n is equal to 5, because the formula is like, your formula is like this for R chart, right? UCL is D4 R bar, center line is R bar, LCL is D3 R bar. So you need to find D4 and D3 from the table. N is equal to 5, D3 is equal to 0, and D4 is equal to 2.115. You substitute this parameter into the formula, right? Okay, D3 is equal to 0, D4 is equal to 2.115. Okay, UCL is equal to R bar multiplied by D4. R bar is equal to 0.023. D4 is equal to 2.115. So you got this number. And then LCL is R bar D3. Since D3 is equal to 0, LCL is equal to 0. And R bar is equal to 0.23. So you need to draw the R control chart. This is LCL is equal to 0 and UCL is equal to 0.049, right? 0.049. You put it here. That is UCL. And CL is equal to 0.023, right? Sorry. 0.023. So you put it here. And then you have to plot each R, right? You have each R, Ri, into the R control chart. The first R is equal to 0.038. 0.038, put it here. And then the second R is equal to 0.019. 0.019. And then continue. Okay? Continue until all 25 data are plotted into the R control chart. After that, you can see that all the data are located within UCL and LCL, right? All the data are in the control limit or are in the control chart or in the R control chart. It means that for the R control chart, it is in control. The process is in control according to R control chart. Okay, this is the first step. And then you need to find X bar control chart, X bar chart or X bar control chart. Because the formula that you have to use to calculate UCL and LCL is UCL is equal to X bar bar plus A2R bar. LCL is equal to X bar bar minus A2R bar. So you need to find A2. Since n is equal to 5, A2, n equal to 5, A2 is equal to 0.577. Okay, 0.577. You substitute this number into the formula. So first you find X bar bar. You have already found it, right? X bar bar is equal to 74.001. So you take that one here and substitute into the equation. 74.001 plus 0.577 multiplied by 0.023. You got this number as UCL and this number as LCL. And this is X bar bar is central line. So here, this is your UCL and this is your LCL. And the CL or center line is 74.001. Again here, you need to plot X bar I from 1 to 25 into the X bar chart. The first X bar 1 is equal to 74.01, 74.01. And the second X bar 2, 74.001. Right here, right? Okay, you continue until all 25 data are plotted into the X bar control chart. Once again, all the data are in the UCL and LCL control limit, right? Okay, no point go out of this control limit, these two control limit. So it means that the process according to X bar chart is in control. Okay, if there is just only one point go outside this control limit, it means that the system is out of control. Okay, so but according to our data and according to the X bar control chart, you can see that there is no out of control. So you can conclude that for X bar chart there is in control. It is in control. So R chart is in control. X bar chart is in control. Both charts are in control. It means that the process is in control. Okay? If there is just only one chart is out of control. For instance, suppose this one is out of control and this one is in control. It means that out of control. Okay? Or this one is in control. This one is out of control. It means this is again out of control. If both out of control, meaning that this one is out of control. Right? Either one is out of control, it means that the process is out of control. If the process is in control, it means both X bar and R chart must be in control. Okay, so this is your assignment. Okay, very simple. N is equal to 4, right? And the number of sample is 20. Draw X bar and R control chart. Check if the process is in control or out of control according to the information given. Okay, very simple. Good luck.